a look at interpreting truth tables. Now, this sounds worse than it really is. A lot of time people are trying to make a statement, say something. They don't always mean what they say. And it's very important that you learn to say exactly what you mean and mean exactly what you say. And that's kind of where we're going to take a look at the logic here. Now, what we're going to take a look at is called the biconditional statement. And that simply means that if one thing happens, then another thing happens. And if that other thing happened, then the first thing had to happen. For example, if you were told by your parents that you could go to a movie tonight if you cleaned your room, and you were observed at the movies, does that necessarily mean that you cleaned your room? Not necessarily. You might have, or you just might have ducked out. Okay. Ducked up. So, it's that kind of an idea that we're looking at here. So, what I want to do here is we're going to very slowly talk through this and work through it. So if I want the converse of this statement, that is simply going to be just flipping it around, right? So that means if x is less than or equal to 2, then x squared is less than or equal to 4. Now what I want to do here is I want to determine if these things are actually true. So I look at the original statement. If x squared is less than or equal to 4, then x must have been less than or equal to 2. So if I choose a value that when I squared is less than 4, I had to have chosen a value that was less than 2. So, you've got truth. What about the other way around? Converse. If I pick a value that is less than or equal to 2, then if I square it, do I get something less than or equal to 4? And again, the answer is going to be what? I don't know. Which one is it? Could be false, could be true, right? Well, yeah, -3 squared, most definitely. So this would have to have been false, okay? So if I want to go and do this biconditional statement, what we basically do is we use both of those, and we use something, a new kind of language that you're going to see quite often. X squared is less than or equal to 4 if and only if x is less than or equal to 2. Now, the shorthand way of writing this is going to look like this. X squared less than or equal to, and I'm not stuttering with my F's here. That is the way it is written. So, the question here is that x squared is less than or equal to 4 if and only if x is less than or equal to 2. That means it goes both ways. If I pick a value for x and I square it and it's less than 4, then it was less than or equal to 2. If I pick a value for x that is less than or equal to 2, when I square it, it will be less than or equal to 4. But is this always true? No. This is false, and if we set that x is equal to, say, -5. That is a perfect example of it, because -5 is less than or equal to 2. But if I take -5 and square it, I get what? 25. And 25 is not less than or equal to 4. So that would end up having to be false. This is a truth table, and what you need to make sure that you put into your little books, and I'll give you a little bit of time to take care of that, is this part of the information. This gives us a starting point. If we have one hypothesis and one conclusion, this outlines all possibilities. So I'll give you a few moments to go and take care of it. All right. Now, this might look a little strange. We set it up so that we identify all possibilities that there could be when we make a statement. Now, when we are making statements, we are not setting it up as maybes. There is no such thing. It's either is or it is not. It's true or false, yes or no. This is a very black and white situation. So the hypothesis could either be true or it could be false. Would you agree with that? Conclusion is either true or false. So because that is the case, there are four possible things that we have to look at. Hypothesis is true, conclusion is true. Hypothesis is true, conclusion is false. Hypothesis is false, conclusion is true, and hypothesis is false, and the conclusion is false. Now, when we are looking at the statement, if P then Q, so Q follows from P. If I have this, that's what happens. You'll notice if this is true, that's true, that's true. Well, that's what you would expect, correct? And if this was true and that's false, that's false. That's what you would expect. Now, the next two usually bother people quite a bit because how in the world can these statements be true if this was false? We cannot proceed from a false assumption. We cannot make a false statement and then figure out anything. So the logic of these things is assumed to be true. It's just the way it is. So you got to make sure that you have this down. Because when we're talking about truth tables, we're always going to be starting with this hypothesis and conclusions for things. So I want to complete a truth table for that thing that we were talking about. So that means that either the hypothesis is true or it's false. Conclusion can either be true or false, true or false. Now, the first thing that we're going to do when we take a look at the statement, that is going if this, then that, right? That's P, then Q. So, according to what we had back here, true, true gets to be true, right? True, false gets to be false. So, true, true, this is going to be true. True, false is going to be false. We don't care about what these things necessarily are. I just know one is P, one is Q. If it's true, true, this is what we get. If it's false, false, that's what we get. Okay? So, false and true gives me what? True. And this gives me true. So, that is the truth of that statement. Now, if I do converse is when we flip things around, right? So for those of you paying attention, I really got to kind of go from this here to this, right? So true, true would be true. False, true would be true. True, false would be false. False, false would be true. Now, biconditional only works with and. And means both, right? Okay. True and true. True. False, true. False. True, false. False. True, true. True. So what we've managed to do here is determine when this is a true statement. Okay? It is only a true statement if we choose an X that makes hypothesis true and the conclusion true. If we have a value that makes either one of these two false, the statement is false. However, if we make a statement that both of them are false, then again, we're still getting it true. That's usually what these bugs be. Looks a little odd, but don't worry. We just kind of keep on going with this, and it'll slowly work itself out. This is one of these things where the more of it you do, the more sense it begins to make. Now we are going to be talking about compound statements. A conjunction means and, a disjunction means or. Now we just said it a few minutes ago that and is you get both, right? If I had eggs and bacon for breakfast, what did I have for breakfast? Eggs and bacon. If I said I had bacon or eggs for breakfast, what did I have? I might have had bacon. I might have had eggs. I could have had both, but what if I had neither? No, I would have to have it at least one of those in order for the or statement to be true. So, here we go. It does a clothing store accepts cash or credit cards but not personal checks. It gives discounts on all cash purchases. Consider the statement. A customer makes a credit card purchase and a customer gets a discount. So, what we do is we are going to identify credit card purchase as what? P or Q? P. And discount as Q, because if you use a credit card, then you get a discount, right? Right. So, this has got to be true. Oops, sorry, wrong color. It's got to be true, got to be true, got to be false, got to be false. Over here, this is going to be true, false, true, false. So now, if this statement is true, 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 false, 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 true, false. What about false, false? What will that be? True? Why? That's what the table says for and, that it has to be both. What do you mean it could be? You would have to do this for every time that you are going to go and do a truth table. Whenever you have to do a truth table, you got to write all this stuff out. Trust me, it makes life a lot easier. And this does get used in quite a bit of programming and electronics. You're trying to figure out whether it's a yes or a no. So, well, yeah, but you're still going to have to write it all out. I expect you to have that in your little book so that you've got a guide to go by. So, if it's false, false, is it true or false? Considering the only way for an and to be true is if you have both. True. So, this is false, so it's going to have to be false. The only way that true for and is if both are true. If one or the other is false, it's false. Okay? That's the way to. So, clothing store accepts cash or credit cards but not personal checks. It gives discounts on all cash purchases. Consider the statement. Customer makes a credit card purchase and the customer gets a discount. Is this going to be possible? No, it should not be possible because making a credit card purchase is fine, but it's supposed to be a cash purchase, right? There you go. So, let's take a look at the or part. Now, if I'm going to fill this out, I am going to have to do the same thing all over again. True, true, false, false, true, false, true, false. Now remember, our and turned out to be true, false, false, false. After a while, it gets pretty easy to go and pop these down, isn't it? No, because and only works if both of them are true. What you're looking at is if then, if this then that. That's a whole different thing. If then and oh gosh yes. So what about or? So now or gets to be if one or the other is true, correct? So is it true for both? Yeah. Is it true here? Yeah. Is it true here? Yeah. Is it true here? No, it's false. So this gives you kind of a way to go through and figure out what would happen. Is a statement true or false? Okay. Gives discounts on all cash purchases. Now, did the statement say that they made discounts only on cash purchases? No, doesn't say that at all. So, given that, is it possible to make a credit card purchase and get a discount? Yes, it would be. Okay, because that discount wasn't exclusive to just that.
Sorry for the interruption, but all I just this is underdog in the comments. Riley Olson, Joey Wagner, Baker Bukowski, Kaya Garces, William Murphy, Jonas, David Jurek, Eli Johnson, Cole Anderson, Kira Mullen, Ray Norman, Matt Tia, Tina Nelson, Allison Hagan, Tyson Gustafson, Emily Comstock, Ron Wilson, and Tony Sherman.
Okay, I'm going to give you I am going to give you 2 minutes, and I want you to see what you can come up with for these 3 statements. All right, here we continue on. So, if I want the converse of this, that means I got to flip things around. So it would look like this. If quadrilateral, okay, is a rhombus, then it is equiangular. Now, the question that we have to have here is this a true statement or is it a false statement? Okay. Well, first off, Ann, is the original statement true? Why? Could be a square. So a square is a rhombus because a rhombus is defined as something that has 4 sides that are exactly the same, correct? And a square is equiangular, so sorry, you're a rectangle. That would absolutely work because it was equiangular, all 4 are right angles, but not all the sides are the same. So that statement is false. Is the converse true? So if I have a rhombus, it's got to be equiangular. What would be an example of something that would have 4 sides that are exactly the same? What would happen if I made a diamond? I'd get a rhombus, right? Because all 4 sides would be the same. Would all the angles be the same? No. So this would have to be what? Converse also has to be false. So now when it comes to writing the biconditional statement, and we can write the biconditional statement, that's not a problem. We just write it as quadrilateral is equiangular IFF, if and only if it is a rhombus. Okay? So, this would end up having to be false, simply because just because it's equiangular doesn't mean it's a rhombus, and just because it's a rhombus doesn't mean it's equiangular. So we've got to be really careful about how we go and look at these statements. Okay? Usually what we want to look for is this idea of a counterexample, something that makes it false. And usually students are really good at trying to find poke the holes in the theories, right? So we kind of go off of that. So let's talk about this since we're kind of running short on time. A chef special at a five-star restaurant offers its customers a complimentary appetizer based on their choice of entree. If a customer orders a filet mignon, they receive leek soup for the appetizer. If the customers ordered grilled salmon for the entree, they receive baby spinach salad for the appetizer. Now, we need to write a truth table for this, and I'll show you what we're going to do. The first thing that they're talking about is the filet mignon, right? Yes, small little steak with that's been trimmed and it's just, yeah. You'd rather, trust me, you'd rather have a porterhouse. So, the filet mignon, we're going to call that P. And what goes with the filet mignon? The leek soup. So that turns out to be Q. And now, I have no idea whatsoever about what P and Q are. All I'm going to do is go P, and it's going to be true, true, false, false. Now I go Q, and that's going to be true, false, true, false. I'm going to set this up for the P then Q. So it'd be P then Q. So that'd be true. This would be false. That would be.
Also, the free Friday winners are Blake Swampa and Morgan Anderson. You can find it this time.
Remember, if you go from a start with a false, if then. Okay? That's what's going to end up happening. So, here we go. So what ends up happening if they have, what if they order salmon? What happens? Okay, if they order filet mignon, they get what? Now what happens if, okay, I do it the other way around? I want to figure out what, say, Q then P is. So this would be true, this would be true, this would be false, this would be true. Because remember, if then, whenever you're going from a false situation, goes that way. Okay? So now, if the situation is such that P and Q have to go together, that's the biconditional statement. If I walk into the restaurant and I see somebody with leek soup, what did I know they ordered? Mignon, filet mignon. And if they're eating their filet mignon, what did I know they got as an appetizer? Leek soup. So that means it's going both ways. And so this turns out to be true, that turns out to be false, that turns out to be false, and this turns out to be true. And you're kind of going, well, what do you mean? Well, if they didn't order filet mignon, they did not get leek soup, correct? That's the false. True would be having it, false would be not having it. Okay? So, I'm going to let you guys get to work on the assignment. We can talk obviously more about this on Monday, but we do at the end of class on Monday.